Welcome to the video for problems 5.1a and 5.1b of Engineering 623. In problem 5.1a, well, actually in both of these problems, we are designing L networks to match a load to a line of characteristic impedance 100 ohms driven at 3 gigahertz. And in problem 5.1a, the load impedance is 150 minus J200. In problem B, it will be 20 minus J90 ohms. But first for 5.1a. So again, in this problem, ZL is equal to 150 minus J200 ohms, and the characteristic impedance of the transmission line is 100 ohms. So the normalized load impedance, which is ZL over Z0, is 1.5 minus J2. And so since the real part of that is greater than 1, that will lie inside the 1 plus JX circle, and therefore, according to your textbook, you should use the L network shown in figure 5.2a on page 229 rather than the network shown in figure 5.2b. We'll be using that one actually in the next part of this problem. But in this case, again, since RL, which is the real part of ZL, this is the normalized load impedance, since the real part of that is greater than 1, we are inside the 1 plus JX circle, and in that case, we want to use the L network shown in figure 5.2a. And that L network will have roughly this kind of form where we have here as our load, and we first have a parallel element and then a series element. And we want to find out what the parallel and series elements should be to match that load to the transmission line. So the way we do that in this case is the following. We find this normalized load impedance on the Smith chart, and that is shown by the red dot here. You can see it here, this red dot at 1.5 minus J2. Then we draw the SWR circle through that point, or another way of saying that is the circle through that point and centered at the center of the chart. And we identify the point diametrically opposite that, which is opposite of 1.5 minus J2. And this is the point shown in blue. Right here, it's along this green arc. You'll see the blue point. And that blue point we can see lies inside the rotated 1 plus JX circle, or so for admittance. Now, this blue point, the red point is for the normalized load impedance. The blue point will be the normalized load admittance, and you see that it's inside the 1 plus, the rotated 1 plus JX, what the book refers to as the rotated 1 plus JX circle. And so we want to get to that circle, and we can get to that circle in either of two ways, going in this direction and intersecting at this green dot, or going in the opposite direction, going in the counterclockwise direction, and intersecting the circle with that green dot. So that's described in the next two steps. We say after finding the blue dot in step 3. Actually, I've labeled a step 3 again. That doesn't really matter. Just know that the next thing you should do is draw on the admittance chart this rotated 1 plus jx circle. We've done that. And then moving along a constant resistance curve, move from the blue point to this second circle, and I say green point. And as it was already mentioned, if we move clockwise, we get one green point. If we move counterclockwise, we get another green point. So we have 2 green points corresponding to 2 possible solutions. And we draw a circle through, now the same circle will go through both green points. And so I'm talking about the circle that is through either of the green points and centered at the center of the Smith chart. That circle that goes through one of them will go actually through both of them. And we identified the circle, identify the point on this circle that is diametrically opposite of the green point, and we'll make that a black point. And so you can see for the upper green point, the diametrically opposed black point is down here below, and so it's the lower black point, and for the lower green point, the diametrically opposed is the upper black point. And then we want to go back to the origin. We want to see how we can go back to the origin to get our match, because remember, we want to match the transmission line. So we'll see what is necessary to get back, and that is shown, is discussed in step 7. Move along a constant resistance curve to the center of the chart. So those are the steps that we have to go through. And now in to these steps, actually, in the process of doing those steps, it may not have been apparent, but we actually identified the values for B and X. The first move we made from the blue point that was inside the admittance circle to the 2 green points, that was determining B. In when we work with this model in part A of the figure, I mean figure 5-2. So when we work with the network in figure 5.2a, we find B first, and then we find X. So B is determined by how far we have to move going from the blue dot to the green dot. And so to go, we can either go in the positive direction, 0.105, that's in the clockwise direction, or we can go in the counterclockwise direction, 0.740. Either one of those will bring us to one of these green dots. If we go 0.105, it goes to the upper green dot. If we go minus 0.740, we go to the lower green dot. So these are the 2 possible values for B, 0.105 and minus 0.740. And then, so that gives us B. And then as we've already said, when we go to the diametrically opposed black points, then we will want to see what's necessary, what kind of a movement or what magnitude of movement is necessary to go back to the origin. And since these 2 points here are symmetric about the origin, we get symmetric values for x here of 1.75 or minus 1.75. Of 1.75 for the first, minus 1.75 for the second. So and one other point to clarify here, the first value is positive 1.75 because to get from the first black point, which remember the first black point is actually the lower black point, it's the one associated with the upper green point. So the first black point is the lower one, and we go in the clockwise direction to get to the origin. So that's why this is positive 1.75. On the other hand, for the second one, we go in the counterclockwise direction, so that's minus 1.75. So we have one solution, which is b equals 0.105, x equals positive 1.75, and then we have a second solution, which is b equals minus 0.74, and x equals minus 1.75. And once we have these values for b and x, we can find the corresponding circuit elements. We just have to remember that positive B represents a capacitor, while negative B would represent an inductor. On the other hand, positive X represents an inductor, and negative X represents a capacitor. And so the rest of this really just consists of algebra, and we end up getting, for the first solution, where we have b equals 0.105 and x equals 1.75. Okay, b equals 0.105 corresponds to a capacitor of 5.57 times 10 to the minus 14 farads, and x equals 1.75 corresponds to an inductor of 9.28 times 10 to the minus 9 henries. And so the L network corresponding to the first solution is this. But if we use the second pair of values, since B is negative, that corresponds to an inductor. And plugging in the formula, we get L equals 7.17 times 10 to the minus 9 henries. And the negative value for X corresponds to a capacitor. And so, and this is a capacitance, 3.03 times 10 minus 13 farads. And so in this case, the inductor is in this position corresponding to the B, and the capacitor up here corresponding to X. So this is our second L network that would work for the given load impedance. So that's how we would handle the load impedance given in problem 5.1a. And now for 5.1b, as we've already said, in this case, the load impedance given is 20 minus J90 ohms. The characteristic impedance is still 100 ohms, so the normalized load impedance in this case becomes 0.2 minus J 0.9. And this will lie outside the 1 plus Jx circle. So now we want to use the network shown in figure 5.2b on page 229. And in this case, if for that network, we find it's like this. We first have a series element. This element is in series with ZL, and then we have the admittance. And so we need to find X first and then B, rather than B first and then X. So the procedure will be a little bit different in this case. We find our normalized impedance on the chart in red, and you can see that down here near the bottom of the Smith chart. Again, that is 0.2 minus J 0.9. And then we will move to the admittance chart by rotating along this blue arc. And you see that we can get to two different points on the admittance chart, and that will correspond to our two different solutions. And remember now that the distance that we have to go is now X. So we're finding X first this time. And we can either go, as we'll see, 0.5 or 1.3. Those will be our two values of X to get these two blue dots. And then once we find that, okay, as we say, draw on the admittance chart the rotated 1 plus JX circle. That's done. Moving along on a constant resistance curve, move from the red point to this circle to get the blue points. That's done. Now draw the circle through these points and centered at the center of the Smith chart, and that's been done up here. The entire circle, every bit of it hasn't been drawn, but the important parts have been drawn. And then on that circle, find the diametrically opposed points. So you see the two green points corresponding to the diametrically opposed to the blue points. So that's discussed. And then once we get to those green points, again, we'll move to the center of the Smith chart to get our match. And when we do that, we find out what B is. And in this case is the two values of B that are symmetric, -2 and 2. So our first solution corresponds to X equals 0.5 and B equals -2. Our second solution is X equals 1.3 and B equals +2. Again, we plug these values into the appropriate formulas. So for the first solution, X equals 0.5 represents an inductor, and since B is negative, that also corresponds to inductor, and both of these inductors would actually have exactly the same value. So that solution is actually represented by this: two inductors, 2.65 times 10 minus 9 henries. On the other hand, the second solution, X equals 1.3 and B equals 2, okay, X equals 1.3 is positive, that corresponds to an inductor. B is equals 2 is positive, that corresponds to a capacitor. And so if you plug in the values for that one, we get for the second solution, we get this L network. So that shows how to find these L networks in the two cases where RL is greater than 1 and RL is less than 1. And so that concludes our discussion of problems 5.1a and 5.1b.